Good morning, everyone. So, as I sent you an email that related to your Saturday topic, those who have not completed or those who have not undertaken any research or industrial experience, the first list or the first Excel sheet has to be provided with the name, the duration, the guide name, and the roll number and the work you have done. Okay. Those only who have not completed, for them the options are given that you can either do the experience now or later in the coming 2-3 months, or you can choose for any equivalent subject. So those who have already completed, they don't need to opt for the subject. And as your seer said, that he has talked to HOD sir and the elective subject will be decided. So I think you don't need to worry for the subject. But for the time being, you please fill the information so that we can understand. And your seer need to send me and I'll be sending it to HOD so that we can understand that how many students have not completed and how many number of students will be allowed for a subject. Okay. So let's start today's class, and I can see that most of you are not present in the class within the very particular time. Okay, so you are final year students, na? So please try to be more punctual with time, because after this class, after this semester, you will be, maybe some of you will be joining some company, you will be joining some business or whatever, and in that case you will know the importance of the time. So please try to maintain some timing. Okay. So with continuation of yesterday's topic, we have discussed yesterday that we are now in this fourth chapter, we'll be dealing with the two basic aspects. The first one is for the storage aspects of the gas storage aspect of the gases, and second was is the transport of the gases, okay, from the coal methane reservoir. And we have seen there are different parameters. Each of them need to be discussed, need to be understood clearly, and for that we have started the detailed discussion. So yesterday we have started the gas storage in the coal matrix topic, okay, and we have seen that the Langmuir isotherm is a fundamental concept that we need to know for the gas storage in the coal matrix. Okay. Now, continuation of that, if we know that if we have established the Langmuir isotherm, or the relation between the pressure with the gas storage capacity at a particular temperature at the composition of the gases, maybe only one gas or maybe 2 or 3 different gases, then only we'll be able to understand that what is the isotherm. Okay. But then we need to understand that what are the factors that again going to govern this isotherm. Okay, because when you are doing the experimental part, or when you are going to do the disruption kinetic testing in the field, so in that case also there are several factors that are going to be important for showing the gas absorption capacity with the pressure. Okay, so let us now see that what are the various factors that are going to affect the absorption isotherm. Okay, if you have seen the equation as they have taken the DAB basis, so obviously in the coal, in that case also, if you have not considered the DAB basis, if you are going to consider the moisture basis or any as received basis or any general total weight basis, then also this parameter will be very much important. Okay, why? Let us discuss. So first is the ash content. Now the ash content, you know what is ash. Okay, so you know that in a coal, the percentage of ash is if it is increasing, so obviously that type of coal is not very much mature, that type of coal is not very much of high grade. Okay, this thing you already know. So if any composition in composition of the coal, different coal type, the gas percent, the ash percent is higher, then obviously the gas storage capacity will be very much less, because the gas storage capacity is dictated by the pore structure in the coal matrix. But if the percentage of coal in the percentage of the carbonaceous matter in the coal is very less, then obviously the gas content will be, gas storage capacity will be also very less. Okay. So what does it mean? That suppose there is a 100 cc volume and the ash percentage is going to increase from 20% to 40%. So what will happen? So what will happen in that case? In that case, you will see that your total carbonaceous content, which is supposed to be present in the coal, that is also going to be very much less, because the gas percentage is going to increase, because the ash percentage is going to increase, and as the ash content is increasing, so obviously there is a chances that if everything is remaining the same, the carbonaceous content, the fixed carbon content or the carbonaceous content, which is actually having the porous matter or the coal matrix, that is also going to decrease. Okay. Now they have given an equation about the mineral content, and they are going to consider this ash content with the sulfur content, and they have expressed the equation as in given in equation 4.2. Okay. But again, I am telling you that other than the Langmuir equation, which is discussed earlier, you don't need to remember all those equation. You can very well understand the equation, and you can know the parameters, and that will do. The importance of the parameter on that equation of the gas storage will be, it will be okay for you if you have understood this. So you can see that the mineral content, because ash content and sometimes the coal is very much content with the sulfur. So the sulfur content is taken together with the ash content and depicted as the mineral content. If the mineral content is going to increase, that means going to decrease. So the total gas retention capacity is having a detrimental effect due to the ash content. As the ash content increases, the Langmuir capacity or the gas storage capacity decreases. Okay. Next parameter is the moisture content. As you can see, the moisture content is nothing but the water content that is already being there in the reservoir. Suppose you are going to collect a coal sample from the reservoir at 1 kilometer depth. Okay. So you have collected the coal sample, but if you are not going to wrap the coal sample with bubble wrapper so as to preserve the moisture at the in situ moisture. What is the in situ moisture? At that pressure temperature condition. Pressure temperature means that at that very depth, whatever moisture is supposed to be there in the coal, if it is saturated with that, you want to keep that moisture. Otherwise, if we are going to take the coal sample without wrapping to the surface, its inherent moisture is some moisture is going to go elapse in the atmosphere. Okay, it is going out, venting out. So in that case, you will think that when you are going to test the laboratory experiment, you will find that okay, sometimes the moisture is coming as 3%, but this 3% was not the actual one. Maybe in the earlier case, it was having 6% or 10%, but as you have not wrapped the sample, you have taken out to the surface, some of the moisture is going to be evaporated by the temperature increase or by the pressure release. Okay. So for that thing, you need to wrap the sample with bubble wrapper. What the moisture content will do? Now the moisture or the water content, they will fill the pore with water. Okay. If the water content or the moisture content in the coal is going to increase, that means whatever the pore spaces available or the void spaces available, that is being filled, some part of that is going to be filled by the water particles. So when the gas particle will be coming, gas particle will not be open to the 100% of the total pore volume that is accessible to them. Okay. So in that case, what will happen? Some part of the total pore volume will be already filled with the moisture, and so only some of the remaining part, maybe some 70%, maybe some 60%, or maybe some 80%, depending on the water saturation, depending on the moisture saturation, only available to the gas particles. So obviously, the gas storage capacity will be also less because the storage is going to be very much less. Storage spaces is going to be already filled by the water particles. So that's why it is always considered the detrimental effect of the moisture onto the gas storage capacity. As the moisture percent increases, the gas storage capacity is going to decrease. Now again, as I mentioned about the saturation, so depending on the water saturation, depending on the inherent moisture, okay, depending on the mobile fluid, depending on the immobile fluid saturation, this moisture content is going to be affected. Okay, suppose at that depth, 1 kilometer depth, when you are collecting the coal sample, you will find, suppose that the sample is having 10% moisture, but then you have wrapped the sample and you are going to test it in the laboratory. When you are going to estimate the moisture content of the sample, you will see that the 10% moisture is remaining there, okay. But when you are going to prepare the dry sample, following the standard test procedure, you will find that you will not be able to reach the 0% of the moisture, okay, because there are some connate water, there are some inherent moisture, okay, already which is there. You cannot separate that water from the coal or from the rock, any rock. So what will happen? You can find that the 10% moisture after drying, it is only showing maybe 1.5% or 2%. So that, and below that, you are unable to reduce the moisture percentage. So in that case, your 2% moisture is the inherent moisture. The 2% moisture or the 1.5% moisture is the inherent moisture that is always sticked, and that is the due to the immobile fluid saturation. It cannot be moved. Whereas the reduction of the moisture from 10% to the 2% or 10% to 1.5%, this reduction is possible because whatever the moisture or the water content was there, that is going to be evaporated or that is going to be transferred from one place to another place, or from coal sample to venting out to the environment when you have dried the sample. So that is not the inherent moisture, that is just the moisture content, that is just the water content. You have wet sample, you have dried it up and it is just evaporated. So these are the some of the differences, but at the same time, the main effect of the moisture is that it is going to compete with the gas particles, and it is going to block the available pore spaces that can be otherwise taken by the gas particles, and so the gas storage capacity of coal is going to be reduced due to the presence of the moisture. Okay. So you can see in the equation also they have considered the moist gas storage capacity and the dry gas storage capacity. Obviously, the dry gas storage capacity is much more than the wet gas storage capacity or the moist gas storage capacity. Why? Because if you are going to prepare the drying the sample, some of the moisture, which is not the inherent moisture, some of the moisture will be evaporated, and then those pore spaces will be available, those pore spaces will be opened, and those pore spaces will be available to the gas particles, so that some amount of the gas particles will be available, will be accessible, and they can fill these pore spaces. So obviously the gas storage capacity will increase. Okay. So this is the main concept for the moisture. Whenever we will be discussing about the test and the preparation of the sample, we'll be again discussing about the standard test procedure, and we'll be discussing in details about the preparation of the sample for dry sample or for the wet sample basis. Okay. The next parameter is the temperature. What is the temperature? Now, temperature, as you know, that it is the isotherm test. So iso means it is a constant or the same, and therm means related to the thermal temperature. Okay. So isotherm test is just doing the test at a fixed temperature. So if you are not going to fix the temperature, then again then depending on the pressure changes and depending on the temperature changes, you will not be able to bifurcate, or you will not be able to differentiate that whether the changes of the gas storage is due to the pressure only, due to the temperature only, or a combination of both, or there may be any other particular parameters or the properties of the coal or the fluid which is going to be dictated. Okay, so we are only changing one parameter at a time and going to be related with the it is going to be related with the gas storage capacity. So if you are keeping all those parameters same, and then you are going to conduct the acetylene testing in defined temperature, suppose 30 degree, suppose 40 degree centigrade, and then 50 degree centigrade. So what you will see, for a particular rock type, suppose for coal here or the any porous media, suppose for shale also, whatever depending on the coal formation, its porosity is fixed. The total void spaces is fixed. But then the availability of those void spaces to the gas, to the water, that can be varied. Okay, that means that the porosity is more or less a fixed thing which is very much not related by the any other saturation or anything. But whatever the saturation is there for the individual component, like for the water saturation, for oil saturation, or for gas saturation, that is going to govern the gas storage capacity. Suppose if I say that a water percentage or the moisture percentage is only 20%, so that means you will be getting only 80% as the maximum gas storage capacity for a particular type of coal. Why? Because 20% of this pore volume is already filled with the water. So you are getting less, 20% less capacity, then the coal can be able to store. Okay. But if you are going to vary the temperature, you will see that although the total void spaces are not going to vary, but the Langmuir pressure constant, which is the B, and in terms of B, it is also the PL, that is going to vary. Why? Because you already know that the gas, depending on the gas law, there are three gas laws: Boyle's law, Charles law, and the Reynolds law. Okay, I hope you all understand. You all remember this thing. Must have read this thing in your class 12 or joint preparation when you are preparing for the JEE. Okay, so when your temperature is changing, the pressure is also going to change in some fraction. Okay, like the Charles law. Okay, like the Charles law, which is going to give you the idea about the temperature with the volume. The Reynolds law is going to change the pressure with the temperature also. Okay, at the same fraction, if you can remember. So obviously the pressure, there is a detrimental effect. So if you are going to increase the pressure, if you are going to increase the temperature, the pressure is going to reduce, and so the gas which will be stored at this lower pressure will be sufficiently less than the gas pressure, than the pressure which otherwise can be stored. That means for 30 degree, 40 degree, and 50 degree centigrade, you will get the maximum storage capacity at 30 degree centigrade only. As you are going to increase from 30 to 40 to 50, you will see that progressively the gas storage capacity for that particular coal sample or that particular coal reservoir will decrease. Okay, so there is an inverse relation. Okay, inverse relation for the temperature also. Now next is the gas composition. Okay, are you able to follow what I am going to discuss, and you are able to see the note what I have shared? Is it visible to all of you?
Yes, sir.
Okay, so the next parameter is the gas composition. Now for the gas composition, you know that the coalition process, when the vegetative matter is changing into the coal, okay, the coal is formed. The main gas which is very much prominent in that, which is liberated from this chemical processes, is the chemical or the biogenic process, is the methane. Okay, but it is not actually only methane. There are some amount of the nitrogen dioxide, there may be some nitrogen, there may be some other oxides of the, or other oxides, there may be some H2S, there may be some carbon dioxide or carbon monoxide. Okay, so depending on the chemical and the biogenic degradation. So all these gas composition need to be considered when you are going to take out the gas, take out the coal. You are going to calculate the gas storage capacity. You have to first check that whether the gas storage capacity is for a single gas or for a gas mixture of the two different gases or maybe three or other gases. What will happen in that case? When you are going to, you have already seen earlier, you have already seen that for permeability, if there is only one single phase, the absolute permeability will play. But if there is a two different phases or there are three different mixture of the gases or the fluids, then there comes the relative permeability. Okay, then the relative permeability, because there is a competency between the fluids and the fluids and the gas will work, and depending on the viscosity, depending on the fluid velocity, depending on the forces they are going to exert on one another, or the shearing forces, the permeability is going to vary. Same thing will happen for the gas storage also. If there are, suppose the more common gases are nitrogen, methane and the carbon dioxide. If you are going to consider that there are three composition, okay, there are three composition of the gases in your reservoir, then obviously you have to check that what composition of the gas is lying at what percentage. That means in 100%, what is the ratio of the gases? If you are unable to do that, then you will not be able to calculate the individual gas component. You will be able to take the total gas content. Okay, you will be able to calculate, you may be able to calculate the total gas content, but you can never able to get that how much what is the gas content for nitrogen, what is the gas storage capacity of methane, what is the gas storage capacity of carbon dioxide, until you know the percentage of the gas fractions available in that reservoir. It is like the Graham's law, okay, like the partial pressure or the total pressure concept you have learned in the colloidal chemistry chapter, okay, or thermodynamics chapter, okay, in your chemistry. So in that case also there will be concept of the partial pressure and the total pressure. So there will be total gas constant, total gas storage capacity or the partial gas storage capacity based on the different components, okay. And it is observed, you will also see later, that the nitrogen, methane and the carbon dioxide gas storage capacity is going to change in the ratio at the same temperature and the pressure as 1:2:4. Okay, the ratio of nitrogen, methane and carbon dioxide gas storage capacity for different coal at the same temperature pressure condition is going to vary as in the ratio 1:2:4. That means nitrogen capacity is half of the methane capacity for gas, and then again for carbon for higher capacity than the nitrogen and the 2 times higher capacity than the methane. Okay, so this is the ratio. Nitrogen is to methane is to carbon dioxide is equal to 1:2:4. Okay, this is the normal ratio of these three gases. So why it is important to know the fraction? If you are not able to know the gas fraction, you will not be able to get that, okay, when you are going to reduce the water pressure from the borehole dewatering process, as you are going to take out the water, you will be able to see that the gas is coming, but then you have to separate the gases and you have to also know the concentration of the different gases so that you can calculate the partial pressure in the total pressure system, and then with this gas fraction you will be able to calculate the total gas adsorbed in that total pressure system. Okay, so maybe you are going to get the production of 500 cc and you know that the nitrogen, methane and the carbon dioxide are coming as a ratio of 1:2:4, then you can already divide it by the proportionality constant. Okay, so the nitrogen fraction will be 1/7, the methane fraction will be 2/7, and the carbon dioxide fraction will be 4/7 into 500 cc. This will give you the individual gas component for all these gases upon production. Okay, and so you have to know the gas composition, because depending on the variation of the gas composition, depending on the individual gases present in a gas mixture, the concentration in a gas mixture, the gas storage capacity is going to vary. Okay, to give you an example, let us observe one graph. Let us see. Please observe this table and the graph. Okay, they have taken it from some data. You can see table 4.3. It is going to give you the isotherm parameter for the methane and carbon dioxide. Okay, so you can see that their Langmuir volume in the DAF basis and the Langmuir pressure from the experiment and the dry ash-free storage capacity at the reservoir condition, that means at the reservoir pressure condition, they have calculated and they have given here. Okay, so you can see, very well see, that for the first parameter, the Langmuir volume, it is approximately twice carbon dioxide isotherm is varying as a twice of the methane isotherm. Can you see that? Then, but keep in the mind that the Langmuir pressure is not the twice, because it is going to mention that the gas storage capacity is going to be varied in that ratio, not the Langmuir pressure capacity. Okay, because the Langmuir pressure is going to be related with the 50% of the total Langmuir volume, and so the Langmuir pressure will never follow the 1:2:4 ratio. And obviously, if you see these two isotherm, the two fine isotherm, the upper one is for the pure carbon dioxide. You can see in the figure 4.2. This is also the core desorption isotherm result. The upper one graph is the pure carbon dioxide graph, and the lowermost graph is the pure methane graph. Okay, if you see the comparison with the pressure with the dry gas-free storage capacity, okay, then you are readily able to see that it is sometimes it is twice or somewhat much more than the twice. Okay, because the methane graph, pure methane graph, has never reached 400, but carbon dioxide is sometimes higher also, 800 SCF per ton. That means that the ratio sometimes may be even higher at the higher pressure. Why this? If you see the shape of the isotherm graph, please look at for the methane and please look at for the carbon dioxide. You can see for the methane, for some initial pressure, the graph is started with some 45-degree angle, and then it is going to be flatter as the pressure increases. Why it is going to be flatter? These all are the cumulative gas production, because it is going to be increased. This cumulative means the total gas production. Whereas you already know that as the pore volumes are fixed for any type of porous rock like coal, so with different stages of the gas injection or different stages of the desorption, the total number of the gases that can be stored is going to be reduced. So obviously, if you are going to send the same amount of the gases for each pressure step, suppose I am going to consider 5 steps here, you will see that the 1, 2, 3, 4, 5 and 6 pressure steps for methane has been shown here, and there are numerous pressure steps for carbon dioxide, suppose 6 or 7. Okay, so let us imagine the step that for each of the 6 pressure steps, you are going to send 100 molecules of methane for each pressure step, and the pressure steps are increased. In the first pressure, the pressure is 1 megapascal, or suppose here it is showing as the maybe 50, then 100, like that. So suppose it is 1 megapascal, then the next it is 2 megapascal, and so on. The 6th pressure step is going to reach 1, 2, 3, 4, 5, and the final it is the 6 megapascal. Okay, so in 1 megapascal, the total pore space are available, to 100% pore space are available. So whatever gas absorption will take place, each of the gas particle has a 100% chance to go anywhere. Okay, so what will happen? Suppose in this, at the end of this first stage, 20% of the pore space is fulfilled. So remaining is At the start of the second phase, second pressure stage at the 2 megapascal, the porous spaces available are not 100% but only 80%. So the rate is already decreased, but as the pressure is increased, so obviously the gases will store, the gases will be absorbed. Why? Because the pressure is increased. If the pressure is remaining the same at 1000 kilopascal or 1 megapascal, then there will be no such increment. Why? Because it is already saturated at 100 megapascal with 20% of the gas absorbed. So at the end of the first step, at the start of the second step, only 80% of the pore spaces are available. Again, you are going to send the 100 molecules. So now it may happen that as only the accessible pore is going to be reduced, maybe the total absorption at the second stage will not be increased more than the first stage. It will be reduced because the pore volume is also reduced. Accessible pore space is also going to reduce. So you will find that only 17 or 15 molecule is going to be absorbed. So at the end of the second stage, you will find 35% pore spaces, 20 plus 15, 35% of the pore spaces is already filled. So again at the start of the third phase, you will find that only 65%. So again the pore space is going to reduce. So these are the stages. So at each stage, the availability of the pore spaces is going to be reduced uniformly. Okay, uniformly or exponentially, because it is not following the same line, linear line. Earlier it was 20, now it is 15. Okay, so it is going to reduce. So what will happen? The stage absorption is the maximum at the first step. Okay, because the total pore accessible volume is available. Sometimes it is also shown in the second step. Why? Because it will depend on how much particle you are going to send at each pressure step and what is the pressure of that pressure step. Okay, depending on that, your graph shape is also going to change. So you can see that like this, the methane pressure is going to be uniformly just going to be flatter. Whereas if you are going to see carbon dioxide, you can see at the very initial stages, carbon dioxide has taken, if you see the gray pressure, gray icons, it is only taken 1, 2, 3, 4, 5. It is for the decreasing pressure step, so it is the desertion. If you take the void one, void square, it is the increasing pressure sequence points, increasing pressure steps. Okay, so you will see that at the first two pressure steps, okay, the carbon dioxide pressure graph or the isotherm graph is steeply increasing, so the rate is quite higher. Okay, and at this point, at some initial point, you may find that it is not only 2 times, it may be increasing to up to 3 times or 4 times. Okay, at the initial stages, if you are going to see the ratio of the methane and carbon dioxide absorption. Okay, so the ratio of this methane and carbon dioxide is not fixed, is not always maintained as 1:2, like the way I have told you earlier. So it can change. Okay, so at lower pressure step, you can see the ratio of these two graph adsorbed, these two gas adsorbed is much more different than the higher pressure step. At higher pressure, it is much more, it is likely 1:2. Okay, but in the earlier cases, it may reach up to 1:3 or 1:4 even. Okay. Now, the stages or this shape of the isotherm will be dictated by VL and PL, okay, because these two are the parameters, okay, and obviously this shape will dictate that at what pressure how much gases can be absorbed. So as you have seen that if the pressure isotherm graph is also going to change, so obviously the gas capacity is also going to change. Okay, now suppose I have they have discussed here the pure carbon dioxide and the pure methane. What if there is a mixture? What if there is a 50-50 mixture of the methane and carbon dioxide? Okay, then what you will see, if this is the case, if this is the case of a gas mixture, then you need to see that okay, depending on the gas concentration here, which is 50-50 or the half-half, obviously its gas storage capacity will also change. And in that case, you will see that the gas storage capacity is lying in between. The mixed gas storage capacity, it is lying in between. Why? You can see the mole fractions of the carbon dioxide is also given. So they have taken the 3 mole fraction condition. First is 0.3, so 30%, 35% and the 40% of carbon dioxide. So the remaining part is the methane. So they have taken the ratio of methane and carbon dioxide for first mixture as 70-30, for second mixture as 65-35 and for third mixture as 60-40. Okay. And with these 3 changes, they have tried to plot the total gas content. This is the total, not the individual. Whereas if we are going to use the pure one, this is the individual one. Okay, so a lot of things can be interpreted from this graph. Okay, as you can see that for the mixture, okay, even if you see the mixture, let me increase the resolution of this. Okay, if you see the graph very carefully, yes, you can see that the 30, 35 and the 40% of the mole fraction of the carbon dioxide is going to be increased. The way you are going to increase the carbon dioxide fraction, the total gas storage capacity is going to increase. Meaning that the gas storage capacity is increased, okay, when the gas fraction of carbon dioxide in the mixture is going to increase from 30 to 40. Okay, that means that methane or the lower adsorbed gas, because its capacity is very less, and the carbon dioxide is assumed to be a higher adsorbed gas. Okay, because it is going to be adsorbed, it is having very high attraction to the coal. Okay, so in that case you will find that due to high attraction of the carbon dioxide to coal, okay, what is happening? This is the carbon dioxide is going to increase the gas storage capacity. Okay, because the carbon dioxide is highly adsorbed compared to the methane. Okay, so how to understand this graph? You have seen that if there is only methane, this is the graph. If there is only carbon dioxide, this is the graph, the upper one. But now you are going to consider the 50-50. So 50% of the carbon dioxide and 50% of the methane. Where does it will lie? Due to methane, the pure methane will give like this. So the 50% methane will give some half of this, as you can see. Whereas the carbon dioxide, depending on this, okay, if this is your graph, suppose this is your pure graph, so the 50% of the methane, if you are going to consider, it will show you the graph like in the half of this. Okay, so it will lie in this direction. Whereas if you are going to consider the pure carbon dioxide graph, okay, if you are going to consider the pure carbon dioxide graph, then what it will happen? This is the total 100% carbon dioxide. So 50% carbon dioxide will be coming directly superimposing on the pure methane graph. Okay. So if you are going to add this 50% carbon dioxide and 50% methane, you will be getting this middle graph. Okay. This is the way you are going to calculate the mixed gas absorption. And for that thing, you need to do the mole fraction. And this mole fraction is not same throughout the temperature and pressure of the acetone test. So you have to take, suppose you are going to take the mixed gas absorption, at each of the pressure stage you have to see the mole fraction, because as the carbon dioxide and the methane adsorbate rate is different, so even if you are going to send the same molecule from the gas as 100 number of molecules, but depending on the pressure, it is not always possible that 50-50 gas molecules of methane and carbon dioxide are going to reach into the coal. It may happen at times that only 60 molecules of carbon dioxide is going and 40 molecules of methane is going. What may happen that 40 molecules of carbon dioxide is going, then it is going to be different because of the rate of adsorption, the attraction of the coal with the gas. Carbon dioxide is having very high capacity. Carbon dioxide is having very high tendency to be adsorbed than the methane. Okay, so that's why this change is happening. Now now if you have seen this, okay, you have also seen that as the mixture, in the mixture, the higher adsorbed gas percentage, when it is increased, the adsorption rate capacity is also going to increase. Okay, so this is true. Again, you have also seen from this graph that how the shape of the graph at initial stages are also going to vary, are also going to be dictated by the isotherm. And again, how the ratio of different gases can be analyzed from a single graph. Okay, so figure 4.2 is very important figure. Okay, all of you must try to understand the different features of this graph. Okay, if you read the discussion, you will be able to read it in a very careful way, in a very easy way. Okay, so I have just told you in summarizing this discussion. Okay, now this is for the pure gas. Whatever equation we have seen earlier for the Langmuir, okay, let me tell you, this is the equation for the pure gas when only methane or only carbon dioxide or only nitrogen are there. Whereas if you are going to see that there is a mixture, this equation is invalid. Then this equation will be invalid. For mixed gas adsorption isotherm calculation, you have to go for the extended Langmuir adsorption isotherm equation, which is given by equation 4.5. This is the equation. This is the equation. You will see what is the changes. The changes here, if I say, the changes are, you will see that the I subscript is there. Okay, the I subscript is for the particular individual isotherm gas component. Okay, either methane or carbon dioxide, and then J is for the total. Okay, that means suppose if you are going to, if you see this here, I is the individual, that means either 1 or either 2, that means in the methane and carbon dioxide mixture you will be using this equation twice, for Gs methane, gas storage of methane, and for Gs carbon dioxide, gas storage of carbon dioxide. Whereas this J is going to vary because it is going to summation, it is going to summarize the individual adsorption. Okay, so what it will do, the VL you need to calculate. Okay, for individual methane or carbon dioxide, the ash and the water content are same as the earlier concept. Bi, Yi and P is the Langmuir pressure constant, Bi is the pure component Langmuir pressure constant of component I, Bi and Yi. What is Yi? Yi is the mole fraction in the mixture. So the Yi is, you have to calculate for methane or for carbon dioxide. So when you are going to calculate for methane, GSI for methane, this Yi will be Y methane. If you are going to calculate the GSI for carbon dioxide, this Yi will be Y CO2. If you see the this nomenclature, you will be able to understand. But in the denominator, it is seen that 1 plus J is equal to 1 to NC, that means number of component. As there are two components, so for each it will be 1 plus, in the first case it will be B methane, Y methane into P plus B carbon dioxide into Y carbon dioxide into P. So this will be the total in the denominator. Okay, this is the summation sign. Whereas for numerator, it is the individual gas component. Why? As we are going to calculate the partial pressure, depending, because we are going to calculate the partial pressure as in the fraction in the total pressure. So here also we are going to calculate the individual gas absorption, and we are going to see what is the total gas absorption by the each individual component. So that's why this summation is coming, to consider the total gas absorption. Okay, so this is for the case of the mixture. Okay, for mixed gas, this equation is called as the extended Langmuir isotherm relation. Extended means it is not for pure, it is for the gas mixture. And you will see that they have shown a calculation. They have shown a calculation in the next page, and they have calculated GI for CO2 and GI for CH4. As you can see, once you try to understand this equation, this example, you will be able to understand the equation. Okay, so I request you, all of you, to please read this, see the data, okay, and use this so that you can calculate, you can able to understand the equation and how the procedures, okay, because this Langmuir isotherm is the fundamental concept, fundamental calculation procedure for gas storage capacity. So you should be able to understand it for the pure gas and for the mixed gas calculation, okay. If when you see this example, there will be a lot of questions, and if you read this carefully with the graph and the data and which is given in the table, with all this nomenclature and all your understanding in the earlier chapters and the earlier concept of the ash percentage and the water percentage, you will be able to understand clearly about the calculation, okay. So I request you to please go through this example. Okay. It is not that I am going to give you an example. I am going to give you some mathematical problem. But as you are learning this cold bed methane, this is the fundamental equation of gas storage capacity. Okay. So you need to understand. Next discussion. Our next discussion is the measurement of the sorption isotherm. Now the measurement of the sorption isotherm, they have shown here the different steps. Okay, so we'll be also discussing the steps. However, the steps are to be calculated at each time of the isotherm testing. So the testing procedure is will be coming later, but we'll just try to understand how we are going to measure this isotherm step by step. Okay, so let us start. Let me just start with one or two parameters because there is only some time remaining. So first is, what are the different steps? Let us discuss. If you are going to measure the sorption isotherm, the first is that you have to select a sample. Okay, select and prepare the samples as per the procedure, as per the standard procedure. You have to perform the isotherm test, and with the isotherm test also you have to perform also some other test so that you can correlate, or you can determine some of the parameter, okay, some of the important parameter. So what are the steps? First is that you have to select the sample. Obviously, if you are going to do the if you are going to do the cold isotherm testing, you have to obviously calculate the prepare the sample, and for that thing you have to collect the sample from the mines. Now, when you are going to collect the sample from the mines, the procedure is that you have to collect the sample from the freshly exposed roof or the freshly exposed coal sample just after the blasting, or just taken from the coal production phase. Okay, coal production. Why? If the coal is going to be lying there for many days, as there are so many cleavage fractures or the so many open fractures in the coal, the whatever gases are trapped, that gases are elapsed into the atmosphere. So if you are going to collect that sample and you are going to take the laboratory analysis for isotherm testing, you will not be able to get the true result of the in situ gas in place or the gas storage capacity. Okay, so for that thing, whenever you are going to collect the sample from the mines, you have to collect the sample not from the open surface heaps, but it should be collected from the actual production phase. And immediately after collection of the coal chunks having the shining coal surfaces, you have to immediately wrap it with the bubble wrapper so as to prevent the equilibrium moisture at that temperature, pressure and the depth condition. Otherwise, the moment you will be taking out to the surface, the moisture which are supposed to be stay there, they are also going to be evaporated. Okay, and if the moisture is going to be evaporated, the fractures, okay, the pore pressure is going to be reduced. As you can know, the moisture is nothing but the water. If the water is going to be evaporated, the pore pressure is going to be zero, and then the stress or there will be no stress because it is open to the atmosphere. So what will happen? There is a high chances that the gases will be also coming out. Okay, so whenever we are going to collect the samples, there is a condition. We have to write the name of the seam from where we are going to collect. we have to collect the sample as the drilling chunks or the core sample, okay, and then from the freshly exposed roof or the production phase, okay, and the depth, because that depth will give you the idea about the stress, and then you wrap it immediately and then label it and then store it, not in the sunlight, in a cold storage space, okay, not in the sunlight, otherwise again the moisture will dry it up. You have to put it in the cold storage space, preferably in a refrigerator, okay. So this is the way we are going to collect the sample. So let us stop here and then we'll be starting the following discussions in the next class, okay. Any questions for anyone?